Hello everyone, and welcome to NSTA Web Seminars, where you can find live interactive learning at your desktop. Tonight's program is part of our series, Preparing for the Next Generation Science Standards, Planning and Carrying Out Investigations. Our presenter is Rick Duschl. My name is Bryn Slate, and I will be moderating tonight's program, and Jeff Lehman is here to provide technical support during the program should you need it. I'd like to remind everyone to visit the NSTA Learning Center, where you can find over 9,500 resources for science educators. Over a third of those are free. You can add them to your library to access when it's convenient for you. And of course, visit our community forums to continue the discussion not only on the next generation science standards, but as well as a number of science topics that are pertinent to you. The online advisors are there to provide assistance, and you can also check out our free professional development tools to help you organize your professional learning and reach your goals. And it's all available there at learningcenter.nsta.org. And now I'd like to go ahead and turn it over to Ted Willard, who is the Director of NSTA's efforts around the Next Generation Science Standards. Welcome, Ted.
Thank you, Bryn, and thank you everyone for showing up this evening. We're really excited to have Rick Duschl here. I'm going to give you a very brief description of the standards to give folks a chance to have a little sense of how what Rich is talking about fits into everything else. So I'll go through here and just start off with a point of that developing the standards is an effort of 4 organizations, the National Academies, Achieve, the American Association for the Advancement of Science, and NSTA, my favorite. There's a multi-step process that's going on here. The framework for K-12 science education was developed by the National Academies of Science back in July 2011, and that is what is being used to develop the next generation science standards. And Achieve is coordinating that work, and it is being overseen or directed by a consortium of 26 states highlighted down here. And it is these standards that will lead to all the elements that we need for our teaching, assessments, curricula, instruction, and teacher development. And so in the process of developing the standards, there was a public review of a draft back in May 2012, and we're coming up now very soon, I think, in another month or so, a second public draft should release some point this fall. The final release isn't expected till the spring of 2013, so to emphasize the point, it's not out yet. But so we do have a lot of information in terms of preparing for the standards by considering the framework itself. As I mentioned, it was released by the National Research Council at the National Academies of Sciences, and that was a committee of scientists, including some Nobel laureates and a few science and several science educators as well. And it emphasizes 3 dimensions to the standards: scientific and engineering practices, cross-cutting concepts, and disciplinary core ideas. I encourage everyone to take a look at the framework. You can get a free PDF from National Academies Press, the website there. And print copies are also available from NSTA Press, and you can see a link to the NSTA store right there. And the Academies have been nice enough where we're actually going to essentially raffle off a copy of the framework this evening, and as we have some copies available donated by the Academy. The practices that we're focused on are listed here. We'll be tonight focusing on the third of them, planning and carrying out investigations, and in later presentations we will address the remaining ones. I mentioned also cross-cutting concepts. Here's the list of those. And then we have the disciplinary core ideas, life science, physical science, earth and space science, and then something new to science standards in some ways is engineering and technology. And in each of these boxes you can see a little bit of the breakdown of what those are. So here is an example of the standards from the May draft, and I highlighted different elements here of how the practices, the cross-cutting concepts, and the disciplinary core ideas have all been combined together. So we have constructed and used models, that's a practice, to explain that atoms combined to form new substances of varying complexity in terms of the number of atoms. That's a point of the disciplinary core ideas. And then this concept of repeating subunits fits into the concept of patterns. And so altogether, these different elements are being used to form a performance expectation. And so with that little introduction there, we'll pass things on to Rick and let him tell us a little bit about practice of planning and carrying out investigations. Thank you, Rick.
Thank you, Ted, and good evening, everyone, and welcome to this third webinar on planning and carrying out investigations. I'm very pleased to be with you this evening, and I want to say thank you to Ted, to Brian, and Jeff for helping out with the presentation. Ted has given us a nice overview of some of the previous steps, and I want to reinforce the idea that a lot of what we're discussing today the story begins with the preparation of the report, Taking Science to School, Learning and Teaching Science in Grades K-8. I had the pleasure of chairing this committee for the National Research Council, and so I've been living with this and following it through with lots of different orientations. And it feeds into what we're talking about tonight, the next generation science standards, and the three components of the disciplinary core ideas, the science and engineering practices, and cross-cutting concepts. A big challenge for all of us is to begin to think about the coordination of these three dimensions into the performance expectations, but more importantly, into the design of learning environments, our classrooms in which the students will perform. So Ted has showed you this same slide, and again, Taking Science to School was the backbone to the development of the framework K-12 science education, which then is the backbone for the ongoing work with the next generation science standards. I'm also on the leadership team for the writing of the next generation science standards, and I co-chair the Earth and Space Science units for this program. Another word that I want to make about the assessment, the curriculum, and instruction, and what's different, we believe, from these current standards, is the attempts that are being made to make sure that there's a tight alignment between the what it is we're teaching, how it is we're assessing, and what the curriculum is. So the performance expectations, when we look at them, will serve a dual purpose of not only helping us decide about curriculum, but also deciding about the assessment of learning, both at the level of the classroom, but also at the level of the state examinations. An important framing for us to move to in thinking about any of the scientific practices is to review and remember that the guiding focus or the theme within Taking Science to School, and also within Ready, Set, Science, the practitioner's version of Taking Science to School, is that it's guided by these four strands of science proficiency. Our conversation tonight, for all intents and purposes, will focus on bullet number 2, generating scientific evidence. Generating and evaluating evidence as part of building and refining models and explanations of the natural world. I have highlighted in blue what I think are the other practices that we have to incorporate into any discussion that involves planning and carry out investigations. And I think it's important that we always recognize that these practices do not stand in and of themselves for any given lesson or any sequence of lessons. So we'll talk a little bit tonight about how investigations get kick-started by asking questions. We'll talk about how in the midst of carrying out an explanation, part of that involves analyzing and interpreting data. And part of this involves using mathematics and computational thinking to help us get to the outcomes of the investigation. If you've had the pleasure and the opportunity of seeing either the first or the second draft, or if you haven't, when you do look at the materials for the standards, there will be a matrix of the science and engineering practices. In the matrix entry for planning and carrying out investigations, this is a narrative that appears adjacent to the grade bands that exist for each and every cluster of K2 through 5. But take a moment right now and read this and see what the overview is about what planning and carrying out investigations involves. Thank you. So tonight, the outline of my presentation will be first to talk about generating evidence. Then we'll talk about designing experiments. Next, evaluating that evidence. But throughout the presentation, there will be two broad themes that keep coming back to us. And that'll be the role of prior knowledge in scientific thinking at all ages, and the importance of experience and instruction for the learner and for the teacher to move learning along. The coordination of my presentation tonight comes from the information that is found in Chapter 5 of Taking Science to School, which is a full elaboration of that second bullet, generating and evaluating evidence and explanations. At the beginning of every chapter in Taking Science to School, you find the major points or the major findings of the chapter. The first one tells us that children, from the research we have, are far more competent in their scientific reasoning than we first suspected, and adults are less sophisticated than perhaps we've imagined. The implication for this is that we can start children with planning and carry out investigations right from kindergarten and first grade. There's no reason we can't do that. In general, second bullet, children are less sophisticated than adults in their scientific reasoning. However, experience plays a critical role in facilitating the development of many aspects of reasoning, often trumping age. So this speaks to the idea that many people hold a position that you can't do certain science practices until such time that the child reaches a particular age. That's not necessarily the case. They can reason well in those domains that are familiar to them, in those domains where they've had a lot of experience. That's the message here. Scientific reasoning is intimately intertwined with conceptual knowledge of the natural phenomena under investigation. And this knowledge sometimes can act as an obstacle, but oftentimes the knowledge can really help facilitate the children's ideas. And the way I like to describe that is to think about the fact that children may have partial understandings, but as teachers, if we tend to always focus on what's missing rather than what's actually there, we're missing a lot of good opportunities for instruction. Finally, many aspects of scientific reasoning require experience and instruction to develop. Left to their own devices, children will only be able to get so far in their understanding of the natural world and of the patterns that exist within the natural world. For example, many children have a hard time distinguishing the evidence from an investigation to the theory that is sort of guiding the way we look at a problem or what tells us the evidence needs to be. And many aspects of modeling do not emerge without explicit instruction and opportunities for practice, and practice becomes that very important notion. So here's the first poll that I'd like to get a sense of from you tonight. I'd like to know how familiar you are with either of the Taking Science to School report or the Ready Set Science report. So I'll pass it back to Brianne and have you engage in this poll process.
Thank you, Rick. And as everyone will see at the top of their participants window, that your poll buttons are now active. Look under your own name and you'll see a button that looks like a letter A. And if you use the pull-down menu on that button, you'll be able to select A through E to let us know which reports you have read. And Rick, I'll give everyone just another moment to respond here before we lock that poll and publish those responses to the whiteboard so you can see the results. It's great to see all those responses coming in. Thank you so much for responding to this poll. It's exciting to see all of the answers coming in on our poll, and it looks like most everyone has submitted their answer there. So I will go ahead and lock those responses and publish that graph to the whiteboard. Rick?
Thank you. So I see that there's a large number of people who didn't participate in the poll, but of those who did, I see that there's a large percentage of you who have not had the opportunity to look at Ready, Set, Science. And so my first recommendation to those individuals is to secure a copy, and you can do so for free. It's available on the National Academy's website, and you can download it to examine it. It's very, very helpful set of guidelines and instructions and lots of examples that are used in helping teachers think about, the ways in which practices, the ways in which the cross-cutting concepts, and importantly, the way that we're thinking about instruction for science. So let's move on. Thank you for the poll. We're talking about two major shifts that the research tells us about teaching science and in the context of generating and evaluating evidence and explanations, or planning and carrying out investigations. And that is that we're really pushing towards a change in the image of science. We don't want individuals to engage in the classroom as a lone scientist, carrying out investigations that are independent of other important talk and argument, critique, and communication models and representations. My two favorite chapters in taking science to school are the ones that get into about the talk and the argument. And in Ready, Set, Science, you'll find that these are chapters 5, talk and argument, and chapter 6, models and representation. It is this process of both within and between the investigations that students carry out that helps represent the deeply social enterprise of science. Another shift in scientific reasoning as a highly development form of logical thinking that cuts across all domains in the science. It is not, it's content dependent on how that logical thinking takes place. And it's also the case that there's a lot of interplay of general reasoning strategies, knowledge of the natural phenomena being studied, and a sense of how scientific and evidence are generated. So we want to ensure that children have the opportunity to not do things just once around, and that's the idea of building and refining models based on the evidence that emerges from the investigations that they plan and carry out. They can also build and refine mechanisms. They can also build and refine theories. Importantly, in planning and carrying out investigations and how it relates to generating and evaluating evidence is the evidence should be problematized. That means that it should be interrogated. The data should be examined. The data should be examined for whether there's decimal points in the wrong place, whether there's a value that makes no sense in the cluster of all the other values that students got in carrying out an investigation. These outliers, these anomalies, these ways in which we interrogate evidence is a very important part of what it means to do science. So let me ask this question now, poll number 2. The evidence-gathering phase of inquiry includes planning and designing the investigations, as well as carrying out steps required to collect data. Which of the statements below do you think is not a part of generating evidence?
Okay, everyone, your poll buttons are now active so that you can respond to Rick's question there. And for those who have recently joined us, your poll buttons are located at the top of the participants window right below your own name. You'll see a letter A, and if you hold your mouse over that button, you'll have the opportunity to select A through E to let us know which one you think is the best answer. I'd also like to remind everyone at this point that our chat window is closed to participant conversation. You can submit a question to the moderators that we will hold for our next question break. And our chat will open again in just a few minutes when we get to our first break. So at this time it looks like that most people have found that poll button and submitted a response. So I will go ahead and lock that poll so that we can take a look at our responses.
Okay, thank you very much for those results. So we see that there's a number of people who think that asking questions is not a part of generating evidence, and another large percentage of individuals selected E, structuring the data. It turns out that in addition to the items that were in the poll, those in the bottom 3 are all part of what entails generating evidence. That the questions you ask are going to decide what measures you will make, what questions you ask of nature, what questions you ask of the inquiry that you're conducting. The measurements themselves, okay, you can ask questions about developing the measures. Collecting data from the measures will have certain kinds of questions that are dealt with that and help to point us towards acquiring the evidence. Structuring the data, once we have it either through observations or we have it through measurements, means to organize it in such ways that we begin to see certain patterns. The polls that you are taking and the results that you see with the bar graphs is one way of structuring the data, so visually you can see where the high-end frequency counts are in this case. So generating evidence is a complex activity that involves a lot of cognitive ideas. So let's talk a little bit more then about asking questions and formulating hypotheses, which is one of the first practices that was part of this series. As far as how it occurs in planning and carrying out investigations, we want questioning to be an iterative cycle, not a one-time event. It isn't something that happens at the beginning of the lesson and then we don't return to it. In fact, research tells us that if children have the opportunity to begin to refine the questions and revisit their initial questions with subsequent questions after they've begun the exploratory study or after they've begun to collect questions, it is those secondary and tertiary questions that really start to get them pinpointing towards the understanding of the concepts and of the frameworks that are being involved. So, not a one-time event. It's always helpful at the beginning of an investigation to allow the children to have an exploratory study of the natural world with structured observations that lead themselves to now more specific questions and hypotheses. The collection of the data should hopefully lead to new questions and the revision of hypotheses and perhaps to another round of data collection. Asking questions is also about formulating the goals of the activity and generating predictions.
All right, everyone, it looks like we've made it to our first question break. I'd like to provide some reminders before we get started with questions. The first one is that you can turn off notifications of other participants joining the room by following these steps, going to Edit at the top of your page, and then selecting Preferences, General, and Visual Notifications. I'd also like to remind everyone that when we do turn on the chat here in a moment, it will likely move quite fast with everyone's comments and ideas coming in, which will be great. But if you prefer to minimize your chat, you can do so by clicking the small arrow on the left-hand side of your chat window. Or if you'd like to detach and expand your chat panel so that it will be larger and easier to follow, you can use the pull-down menu on the right-hand top side of the chat window and then select where it says Detach Panel. And then you can stretch the sides of the chat box to be whatever size you would like. I'd also remind everyone that although we won't be able to get to all of the questions and all of the discussion here this evening, you can continue talking about this program and others in the NGSS series by going to the community forums there in the NSTA Learning Center. And at this point, I will go ahead and turn on our chat, and we'll pause for a few moments and let everyone submit their questions. Then after we've had some time to view those questions, Ted Willard will select a few of those to present to Rick.
Yes, thanks, Bryn. And we'll get started here. I actually do have one question that's come up already. Peter McFarland is commenting he loves the idea of questions leading to other questions. Does this mean that the curriculum at each grade level will be minimized so that more questions can be explored?
Yes, that's the intent behind the disciplinary core ideas in the design of the framework and in the implementation of the next generation science standards. So Ted had shown at the introduction the categories on subtopic areas of the life science, the physical science, and the earth sciences, as well as engineering and technology. The idea is to begin to focus on the foundational knowledge, and the word that is used in the framework is to say those things that are generative, that is, those things that can build with time and become very important in engaging in, say, biology, the life sciences, or earth science. An example that is used now a lot, because it's been well researched and developed, is the way in which we focus on teaching about matter and teaching about the particles of atoms and molecules. We want to put a lot of limits on the depth to which you go into those ideas. Too much too soon is going to create a word swarm for the children and too many concepts. So by reducing the number of concepts and enabling the children to stay on a particular topic, on an investigation for more than a period, or to think about that investigation being one that in biology and in the earth sciences, may be carried out over several data gathering episodes week after week or month after month, to which the information is then pulled together at some later point in time for the analysis, is an example of how you have a focus and where the additional questions will come. So that was a good question.
All right, next question here is, since the next generation science standards and the framework both include technology as well, how is an investigation in science different or similar to an investigation in technology or engineering?
Another good question. Well, I think as science has shifted over the last several decades and more technology has come in, there's a lot of fuzzy boundaries between the sciences themselves in terms of the problems. Is this a physics problem or is it a biology problem when we're dealing with biophysics? Is it a earth science problem or a chemistry problem when we're dealing with geochemistry? We have the same thing going on between engineering writ large and science. The way we have handled it with the next generation science standards is to think about the fact that science is about working towards explanations of the natural world, and engineering is focused on generating solutions to problems of engineering the natural world. And certainly engineers use science concepts, and certainly engineers conduct investigations about the materials they'll be using to build an engineering structure, be it a bridge or be it a channel of a stream to try and prevent flooding. But it's also how we're building our buildings. You know, there isn't anything in our world that really isn't about the broader technology and engineering idea. But the slide that I showed earlier about the narrative of planning and carrying out investigations captured a kind of the essence of that distinction between the two.
Great. One last question here is, how can we evaluate, or how should we evaluate students in the state when they're engaged in planning and carrying out investigations?
Well, that's certainly going to be the teacher's role, and I think that, you know, the students are going to be generating hopefully artifacts of the drawings they do, the data tables that they construct, that there'll be some kind of a, you know, very popular now for many teachers to have journaling done in the classroom, in which students would keep a science notebook of the information. I think that given the format that we have, I would like to see the evaluation focus on the children's understanding of the relevant concepts that are part of the investigation. What's the evidence that the students recognize the goal and the purpose of the investigation and an understanding of those core concepts? As you saw, that many of the performance expectations are tied to a particular practice. So, you know, carrying out an investigation has a lot of different components to it. And, you know, I would like to see evidence that the student or the group of students who have been given a particular aspect of that investigation have pulled together the necessary information. And then, you know, finally, the evaluation can be one in which we ask the students to use the information and the data that they've gotten from carrying out an investigation to see if they can apply it to a new and novel problem. That would be some of the suggestions that I would have about evaluation of students in planning and carrying out investigations.
Great. We've got a few more good questions in here, but I think we should probably move on at this point, and we'll see if we can come around to them again, one of their other breaks.
Okay. So to talk about collecting and structuring data, I want to present to you a set of lessons and labs that I've done some investigations with. And it's based on a series of lessons that occur over a week. Day 1, Day 2, 3, Day 4, 5, as you can see. And it's called Exercise for a Healthy Heart. This lab sequence was developed in collaboration with the American Heart Association that wanted to get middle school children tuned into what would be the right way to exercise. And part of that is getting your heart rate up to an exercising heart rate. with time, we started to use this investigation to begin to study how children reasoned about data and how children reason about the patterns in data. So I'm going to present to you some of the data that was collected by the students in subsequent slides. And we'll be focusing on the data that was collected on the first day, in which the students were asked to take a resting heart rate and to do so at 4 different periods of time. Take one for 6 seconds, and then multiply it by 10. Take one for 10 seconds, times 6, 15 times 4, and then for a full 60 seconds. When the lab was over, and after they did the next day, 2 and 3, a lab with which is called the step test, where the students would step up and down either one stair on a flight of stairs, or using a step aerobics platform if that was available. And they would do that at a different rate, and then they would do that with different amounts of weight. So we would collect half-liter or quart-size jugs of milk or juice, wash them out, clean them out, and you can fill them either with sand or you can fill them with water, and it simulates carrying extra weight on your body, and you get to look at the impact that has on heart rate. But at the end of the activity, and after the children had gathered all this data, had tabulated all this data, we started asking them questions about the data itself and what matters in getting good data. So here's poll number 3. And this is a poll that we gave to the students in this activity after they were done collecting all this data. We asked them if it matters where you take a pulse, on your wrist, your neck, or your thigh. We asked them if it matters how long you take a resting pulse. We asked them if it matters how long you take an exercising pulse, so that would be immediately after you finish your exercise. And we asked them if it matters who takes a pulse, if you took it yourself or if the person sitting next to you was responsible for taking it. So I'll turn it back over to Brianne for another poll here.
Thank you, Rick. And everyone, we're going to take each of these questions one at a time. So we're going to be looking at the first one. It matters where you take a pulse. And you'll use the green check to agree or the red X to disagree. And you'll notice that that poll button is at the top of your participant window, right under your own name. If you've joined us since we last did our poll. And it looks like lots of folks are answering. The numbers are going up very quickly, so we'll give just another moment for everyone to respond here. It looks like we've got over 2/3 who have submitted an answer. Thank you for doing that. And we're getting close to 100% response rate here, so I'll give just one more moment before we lock our poll and publish those results. And there are the results of our first poll. So Rick, would you like to discuss those first, or should we move on to number 2?
No, let's do all 4 of them, and then we'll look at them together.
Sounds good. Okay, everyone, so that poll is cleared, and we're going to open it back up so you can answer number 2. So look at number 2 here. It matters how long you take a resting pulse. And if you agree, give us a green check. If you disagree, give us a red X. And it's great to see everyone voting so quickly and sharing their response to that one. We've got almost everyone responded, so just one more moment, everybody. And we'll lock that one. and put up those results. And now on to number 3. Our third poll is now active and available. It matters how long you take an exercising pulse. Great job, everyone, with those poll buttons. You're getting faster each time. And the response rate's going up, too, so it looks like we've got almost everyone in there. So we'll go ahead and lock that one and put up those results. And now it's time for our final question, number 4. And those poll buttons are once again active. It looks like we've got most everyone up there. I'll give just another moment before locking question 3 and posting those to the whiteboard here. And here is our final response graph. So we'll try to squeeze it in there, right there in the bottom, so we can see all of them and still see our text. And Rick, back to you.
Thank you. Well, this is exactly the kind of responses that as a teacher in the classroom I would really welcome, because it really gives us something to talk about in terms of the diversity of ideas and the perspectives that exist here back and forth. With middle school children that we've done this with, the only 2 that really came out where they felt strongly and passionately about the differences were questions number 2 and 3. The children didn't really think it mattered where you took the pulse, because some of them would find their pulse on the wrist, and then others would, if they couldn't find it on the wrist, we showed them where on their neck they could find the pulse, and then if you know, the other place that you can locate one is on the thigh, but most of the kids did the wrist and the neck. The children also didn't think it mattered who took the pulse, and so when we move forward in this lesson with the children to begin to talk about the lessons of data, we asked them to begin to think about their results, and here's the results that they got. So if you look at this data for the 6, the 10, and the 60-second, and this is a sample from one of the classes, you can see that there's some interesting sort of patterns of the data based on the 6-second, the 10-second, and the 60-second. Now the kids recognize, at least there were many children in the classroom who recognized that if you missed the count by 1 second in the counting for 6 seconds, let me rephrase that. If you missed the count by 1 over a 6-second period, and then you multiplied it by 10, that 1 count mistake would push you, say, to an 80 rather than a 70, or down to a 60 rather than a 70 in terms of a gap of 10. And so they picked up on that and sort of thought that that was not something that we really wanted to look at. The 10-second, we see other large groupings, again, with 66 appearing many times and 72 appearing many times, and then less frequent. But when we go over to 60, we really start to see a broader distribution of what the data looks like. Now, this data was entered into a software program that's readily available. This would be one of the things that I would strongly encourage as part of your practice and use of technology in your classrooms, is to try and find some software that enables the students to enter their data. But we also know that you don't want to have students entering data into software before they have tried to construct their own representations of the data through their whatever way they want. And the point is that this is part of, exploration of looking at the way in which the measurements take place. And this is part of what data structuring is. This bar graph is one in many ways that students might choose to structure their data. But if we move too quickly into the software, the students won't have the opportunity to reason about the ways in which data displays take place. And this, we'll see a little bit more of this in a few slides into the program, but this is exactly the kind of conversation that takes place in Chapter 6 of Ready, Set, Science about modeling and representation. So let's look at the designing experiments now. In designing an experiment, we can really have three different kinds of categories, if you will. We can generate observations and measurements that before we ask a hypothesis, and based on the patterns that emerge from what the students either observe or measure, they can begin to pose some ideas or pose some conjectures and some hypotheses about what they think is going on. And this is referred to as the discovery context. And it turns out that a lot of areas of science actually do this. One in particular is the studies of the human genome, where massive amounts of data, just huge big data sets, are generated, and scientists just look for interesting patterns in the data first, and then structure a hypothesis afterwards. That's the spirit of this first one, is to just get kids taking a lot of measurements about a phenomena. That helps get them familiar with the phenomena, which we talked about earlier as being very important. And out of that also to connect to the prior discussion about questions would emerge from that as well, I'm sure. But there are many investigations where we test existing hypotheses, and we're looking for a confirmation or a verification context. And this is equally an important kind of planning and carrying out an investigation in science. And then the third one, which is very important for scientists, ascertaining what the cause and effect relationships may be in a science context, is to work with the idea of isolating variables or having control of variables as a strategy for valid inferences. And one of the things that's helpful about the isolating variables is the last part here, is that it serves to constrain the number of possible experiments that need to be considered in conducting these investigations. And that's an important conversation for children to have with themselves and in the classroom. So I said at the top end of the presentation that one of the themes was the role of prior knowledge and the importance of that prior knowledge. So at all ages, the prior knowledge of a domain under investigation plays an important role in the formulation of questions and hypotheses. The more familiar you are with a domain, the more you're going to be able to reason within that domain. So young children, for example, because of their time on this planet, can come up with some pretty interesting ideas and hypotheses about what happens to the food that they eat in their body as they're digesting it. They're very familiar about certain forms of motion, forces in motion, just from their experiences of playing on playgrounds or engaging in sports, or otherwise just moving around in this world. And so the time engaging with the phenomena is very important, again, to stress. And in some domains, students will have this experience, but when they don't have this rich experience with the phenomena, it must be built into the classroom events. And so, this is why, going back to the exercise for a healthy heart, It wasn't about, the objectives were not just about knowing about the circulation and the parts of the body that deal with circulation. It was about engaging in, what do we need to know about pulse rate information that helps us answer other questions. And so after 3-4 times of the students going through the process of taking the pulse and gathering, taking and gathering, they became very intimately aware of what the fluctuation and variance was, what the mistakes were, how to begin to account for them, and to reason effectively. So prior knowledge, and one of the ways we can get at it in our lessons, and I would see this as a task that occurs before you have students engage in the planning and the carrying out of investigations, is finding out what they know. I got this idea of benchmark activities from reading a paper a long time ago from Jim Minstrel, who, former physics teacher, but now a science education researcher, and that these are tasks that are given to students at the beginning of a unit prior to any instruction. And depending on how you want to roll it out with the students, you might give them a choice of how to respond. You may say, draw what you think. You may say, do a label drawing of what you think the phenomena are. You can storyboard it. This is like a cartoon where each frame represents a different step in the action of an event. Children are quite capable of doing those kinds of drawings, and what they say in these drawings, what they communicate, is very insightful as to what their prior knowledge is. Symbols and just downright writing as well. These benchmarks activities, this prior knowledge, is used by the teacher to help target the instruction and to identify learners' common sense understandings, what we sometimes call misconceptions. But importantly, it's also about finding out that you may have some kids in your class who have some really good ideas, really seem to understand the domain already, and otherwise have productive intuitions. This is really helpful as a teacher to know you've got such children in your classroom, because you can use them as a resource with the teaching. So here are 2 examples of a benchmark activity that was used in a curriculum unit on flotation and buoyancy. And I've posed 3 questions at the top of the page for you to look at. When you look at these drawings, what does the child seem to understand? What does the child appear to confuse? And what, in your opinion, is the student ready to learn? So go back and forth between the 2 drawings. And I also want you to look at how the students have used certain words or not used words. I'd like to draw your attention to the arrows and to look at the differences between the use of the arrows in the 2 drawings. I'd like you to think about what you think are some of the confusions that the students have made. And again, this is prior to instruction. This lesson hasn't started. This is what these children knew coming into this unit on looking at the design of vessels that would maximize carrying capacity. And we wanted to find out what they knew about why things float and why things sink. So here's some of the things that you may have listed as a difference. And I'll go back and forth now with each of these so we can see that. With the use of arrows, student 1, which is on the left, uses them to represent lines of force, where student 2 uses them as pointers. Student 1 actually uses the word force, or the force concept in the drawing, as a label. Student 2 does not. Oops, wrong way, sorry. Confusions. Did you notice that student 1 has weight of air acting as a downward force? This is a frequent common sense idea, and he also, or she also, has the gravity arrows showing sideways. Here's the gravity arrows sideways. And below the line. Student 2 has used the symbol greater than incorrectly for the buoyancy and gravity relationship to explain sinking. Right here. When buoyancy is greater than gravity, the object will move up, just as when you release a helium balloon, or if you hold a tennis ball or a beach ball under the water and you let go of it, it rapidly rises to the surface because the buoyant force is pushing it upwards. With respect to guiding conceptions, or what is it that the student is thinking about, or perhaps has as a model of how sinking and floating occurs, student 1 uses a density model, and student 2 uses a gravity equals buoyancy as an explanation for floating and sinking. We get the density explanation here in the written statement that the student uses as they write, things float because they don't have a lot of density. Things that don't float have a lot of density. Density is the amount of weight per unit. And here, in this writing, we see that flotation or floating is equal to the gravity is equal to the buoyancy. Sinking, the gravity is greater than the buoyancy. So the student got the relationship right here in the writing, but didn't represent it accurately with the symbol system used here. And finally, one of the examples of a productive intuition is student number 1 uses the buoyancy arrows to show water pressure acting in all directions. And while the student might not know that that is actually the right way to represent this, it is indeed the case that in a buoyant force with the liquid, at any given point, that force acts in all directions in the water. So what this tells us now is we want situations when we're planning and carrying out investigations where we can tap into the prior knowledge that children bring to the classroom. When we design investigations, when we plan and carry out investigations that are domain general, those are discussed in Chapter 5 of Taking Science to School as being knowledge lean. There's not a lot going on there. An example would be an investigation to look at the law of the pendulum, in which the students are to isolate the 3 variables of length, strain, size of weight, and the height that the weight is released, to determine which variable influences the period, time, and swing. And this investigation can be done in one lesson, and you can find out, what the variables are.
Rick, I'm going to interrupt you for just a moment. The audio quality suddenly went extremely poor, so I'm going to ask if you can just perhaps adjust your microphone and give us another test.
Testing 2.
Okay, I'm still hearing the rough sound, but If you want to pause for just one moment, I'll check with the tech team here to get some ideas for troubleshooting that. Okay, Rick, can you try running the audio setup wizard? We'll pause for just a moment and open up the chat while you do that, but I think that that should address your audio issue right now.
Okay.
Thank you.
Well, Rick does that. I can take a moment and try to address a few of the questions that have come up that are things that I can point to and answer. We had a question at one point about the relationship between National Board and NGSS. I had pointed out that the College Board has a science framework that they had developed, and that was being used by the framework writers and the next generation science standards writers as a guiding document, in addition to some of the previous standards documents in the 1990s, Benchmarks for Science Literacy, the National Science Education Standards. Someone also then asked, they wondered if they were, by National Board, the question asker had been referring to the National Board for Professional Teaching Standards. I don't think so, but the relationship, let me answer that question as well. The National Board for Professional Teaching Standards, usually in their standards, point to how teachers should incorporate individual standards into their teaching and working towards addressing. In most cases, those are state standards or have been using particular national science standards like the NSCS or benchmarks. And once NGSS comes out, I would think that they would be expecting or be looking for teachers to be making use of the next generation science standards in their development of portfolios for MBPTS certification. And so try that. All right, so see if Rick is ready now.
Yes, I'm back. I hope that's better.
That's much better. Thanks, Rick.
Okay.
And thanks for doing that. And I also wanted to take this opportunity to just make you aware of the time. It's about 7:30. So just to increase the pace just a little bit so that we can stay on time.
Yes, I will do that. So I'll just quickly review this slide and to say that there's a difference between bringing experiments in that are domain general and knowledge lean, because that minimizes the role of prior knowledge, as opposed to an experiment which is more domain specific and knowledge rich that infuses the role of the prior knowledge. And that's, in the example is to take the same thing with the law of the pendulum, but now turn it into a problem-based investigation of, can you use the information that's obtained from finding out about the variables and the data that is collected from different lengths of string to execute with the data, building a second timer and finding out then whether that timer with string would then also apply to different materials. And you can imagine that the children now are going to have to think about their prior knowledge about wood, their prior knowledge about metal, and begin to think about whether those factors would, again, apply to the generalizable law of the pendulum. Sequence matters here. It matters the sequence with which students are presented the lessons, and sustained engagement with the phenomena, once again, is essential. The reason is that people talk about the fact that the kids need to have the opportunity to get a grip on nature, that they need to have that opportunity to engage with those materials. So we're back now to the data that we looked at earlier with exercising the healthy heart. And the way we problematize this is we ask the children, what's the range of a normal heart rate? And that they could go back and use any of the sets of data that they wanted to. The students were put into groups. The students then took a lesson period to pore over all the data that they had collected. And within the 5 groups, just to give you a sense of what might happen, what can happen when you allow children this time to go through the process of analyzing the data, this graph shows the results of 5 different groups who came up with, in highlighted blue, 5 different strategies for answering the question, what was a normal range? And you'll see that the results that they got were pretty much the same, 60, 80, 70, 80, 60, 80, you see here, 60, 80, 60, 75, 60, 80. So the results are the same, but the strategies that they used to get there were all very different. And that was amazing to turn and have a conversation then with the students in the groups about the different ways that they went around carrying out the investigation. In Chapter 6 of Ready, Set, Science, you'll find this lovely case study of teaching in of an elementary school in which the results of this investigation were students who started in first grade representing their data this way, and this was a longitudinal study that then followed the students into third grade. And we see here the typical connect the dots kind of a scenario that is very popular when students are doing graphs of the data they have. But what happens if you get a data cluster of all the data that's been collected by the students and you put it into one of these software programs, and then you ask the students, well, where do we draw the line now with all of these data? And in many children, and it comes up, it's not that hard for them to suggest, put it down the middle. And indeed, that's very close to what scientists would do mathematically to get at the regression line. But further on, the students in 5th grade start to shift to a distribution, and this is all about growing plants. Every year, in the 1st grade, the 2nd grade, the 3rd grade, and so forth and so on, these students kept growing Wisconsin fast plants and kept probing different questions about the growth rate and what seemed to enable that growth rate to take place. So that's another factor of carrying out investigations and coming to grips with the phenomena, is that perhaps some investigations should be ones that students see again, but take to a different level of analysis. Each of the times that we collect data, we have to decide what data we're going to keep, what data we're going to discard, whether we have enough data. And when we have this conversation, it helps us arrive at the evidence. Once we have that evidence, we then have to decide how are we going to find patterns in that evidence. And once we find the patterns, we then have to go through the process of saying, well, can we find an explanation for this? Or is our explanation one that is novel, or is it similar to what we might find in the textbook or other areas? I like to suggest this as a kind of, what counts discourse about the data, and to see students engage in planning and carrying out investigations, that they're asking these questions along the way as they're engaged in the data. And each of these transformations of asking, okay, we got the data, now what counts as the data? Do we have to consider it, as I said before, and what's wrong? What are the patterns? And then what are the ways in which it connects to explanations? This is the same sequence that was in the previous diagram, starting with the design of an investigation and the planning of it, the data collection, moving to the evidence, the patterns, and the explanation. The sentences and phrases in this middle column are taken from Ready, Set, Science. And so in Ready, Set, Science, you get some nice descriptions of the ways in which the scientific practices are involved with these kinds of steps that are the broader steps of planning and carrying out investigations. From these practices, we can then think about what we can say are sort of the action verbs of what we would expect children to be able to do, and these can help us generate the kind of learning expectations or learning goals or objectives that we have for the lessons that are part of designing and carrying out investigations. what we find out about the prior beliefs from other studies is that children and scientists, as it turns out, because these researchers looked at both of them, will typically perform any one of these 8 outcomes when they have a piece of data that doesn't fit. And we call that an anomalous piece of data. And this is an interesting thing to pay attention to with your students, is to see how they deal with a finding, a result, a measurement, an observation, a pattern that doesn't seem to fit with what is expected, and to then begin to incorporate that into the conversation.
Okay, Rich, because of our time, we're going to go on from here. But I just want to point out one thing here for those people who were attending last time. If you look at Rick's slide here about evidence, patterns, and models and explanations, you may see some similarities to what Christina and Cindy last time talked about with a pyramid, referring to observations, patterns, and models. And so those of you may want to think about how these two things are related to each other. And so we'll go on to the end here, and we'll do some more questions at the very end. Thanks.
Okay. So this is another example of some research that's been done with middle school children, and this is in the context of life science. And the project is called Promoting Reasoning and Conceptual Change in Science. And what this project looked at was how to look at the ways in which students would reason about methodologies in carrying out investigations: sample size, reliability, accuracy of measures, interpreting data, the kinds of things that we've just been talking about. This investigation was based on this experiment in which students were given eggs that had the shells dissolved off of them, so that it was a simulation of a cell, and the eggs were placed in different solutions to see what would happen as materials moved across into the cell, diffusion into the cell, or information out of the cell. The purpose of showing you this is to sort of look at one way that we can evaluate students' learning, which a question came up earlier. So this would be the data table that the students would complete as they place their eggs in a cup of liquid, one that was containing water and another one that was containing a sugar syrup, and then recording the weight before it went in, and then recording the weight after the egg had been in that solution for 24 hours, and then writing down some observations of what happened to the egg. In one of these conditions, the egg swells significantly, and in another condition, the egg shrivels. The students later on in the investigation are provided more information. They didn't carry out these different investigations. They did do iodine, they did water, and they did the syrup. But they were then also given information about other substances, and they could see the effect that it had here now in the weight of the substance before and after. That data, that experience, that protracted kind of involvement with the investigation was then the basis for asking the students to engage in this final question for the suite of investigations that took place. And they were asked the question at the top: why and how do you think lead is actively transported into cells if it is poisonous? Use a diagram or picture to show your ideas. Use reason bubbles to show the evidence that supports different parts of the model. I'm going to show you 4 of these drawings. They range from what we perceive to be a high level of performance, then a medium high, and a medium and a low level of performance. But here's where we get into this idea of the representations and the kind of ways that we allow children to communicate their scientific reasoning about the evidence that they've gained from the investigations, and how that is used to then characterize a mechanism, an argument, an explanation, or a model representation. We look for all four of those features in these drawings. Here we see one where there's been a key that's been provided. The star represents the lead. There's a calcium channel that they've been taught about. We see the child has indicated that. There's some calculation and communication here, and otherwise a fairly rich kind of presentation for this. Moving further down, we see a different kind of a drawing with a different representation. We can begin to, capture what the student's thinking. Here is what is written down below so that you can read it a little bit easier. But you can see the differences. I'll go back to each of these. The diversity of ideas, which confirms what we know from taking science to school, that in any given classroom, you're going to get a range of diversity in the abilities of the students to understand and communicate the ideas. And that's important to capture and to be able to work with as a teacher. And then finally, here's what we consider to be a low-level response to the lead particle question. And here's how the student has written about it. And this was the rubric that was generated through some ideas that we had. It's a little busy, except that moving from here to here, we get more details, and this is the column to pay attention to. We get more information about the scale in the drawing, the clarity, and the descriptive power as the representation. With respect to argumentation, we see more claims, we see more evidence, justifications. With the modeling as it relates to explanation, we see that it's more purposeful, we see that it's a holistic, and we also look at mechanism, and we see that a high mechanism is more organized and has a schema or mechanistic schema related to it. So I think that, again, this answers partly the question of how to evaluate some of these ideas. So I'm down to the last two slides in the summary, and it's a conversation that I had with a researcher at Vanderbilt University who has spent a lot of time working with elementary school children, and it was her work that I showed you the graphs moving from the first grade to the third grade to the fifth grade. And her summary of what's involved for setting up a model of the world to study the world does not come easy to children. And that's what planning and carrying out investigations are really about. We're studying the world. It helps, according to her, and it's reinforcing some of our points that we've had already, that you need prolonged experience with the phenomena. You need to allow the children to pose and revise questions, working over time to making explicit and refine the criteria themselves for good questions. They need to be involved with parsing out objects and events into attributes that bear on the question. They need to be considering and debating means of measuring attributes in ways that support their models. They need to generate and create data in the ways that we saw those tables from the exercise for a healthy heart. They need to structure the data. Patterns are made. They're not found from the data. They need to interpret the data as evidence. They need to test their models against their original ideas, and then generate, entertain alternatives, look at the fit. And if they do all this, the modeling selection, it usually results in theoretically deeper questions on the part of the students that really raise the bar for the science learning. So I want to thank you very much for the opportunity to share some of my ideas about planning and carrying out investigations. I want to encourage those of you who haven't to seek out Ready, Set, Science. Look at chapters 5 and 6, and you'll see a lot of good ideas and a lot of reinforcement of some of the things that have been presented here. So thank you.
Thanks, Rick. We'll go cut a couple questions here that I've been collecting. Ready, Set, Science itself was for grades K through 8. So sort of two pieces here is, One is, are the recommendations that you're doing here, do they apply to the higher grades, to high school? And what other resources should teachers or students at older grades look to that gives them the same sort of similar recommendations to what Ready, Set, Science does, but appropriate for their grade levels?
Okay, that's good. That's a good question. I think that the main recommendations for from Ready, Set, Science as they apply to K-8 do apply to the high school domain. To look at another source of information that I think captures some of the basic ideas about the learning practices, about the core ideas, is to look at the products from the College Board. The College Board has a book called Science Strategies, Standards for College Success. And in that document, it lays out the same structure or format that Achieve is trying to do with next generation science standards. There's information about middle school and high school for each of the major areas: life science, physical science, earth science. And within those areas, it talks about the essential knowledge, and it also talks about performance expectations. So that's a very good source for middle school and high school to look at. But I think you're going to find that the way our thinking of science learning is similar is because this idea of scientific practices is drawn from studies of the way scientists themselves engage in these practices. And what we're doing or thinking about is, how to adapt those to make them age appropriate in the contexts that are accessible to the learners at that age, so that they can carry out the same sets of ideas that I've introduced for planning and carrying out investigations.
Great, thanks. Another person pointed out, and I think wouldn't be the only one who says that they don't feel their own statistics skills and data analysis skills are particularly strong. Do you have any particular suggestions in terms of professional development or other ways they could improve their own skills so that they can better help their students?
Sure. Well, one of the ways to do it is to start doing it. Some of the statistical practices that I'm advocating here involve nothing more than basic arithmetic: addition, subtraction, multiplication, and division. When we look at the data sets and we can begin to stack things up to see what categories have the most, when we begin to ask what's the cutoff point, half below, half above, when we start to look at the spread or the range, what's the smallest value, what's the largest value, what's the most frequently occurring value, what is the mean or the average. These are not difficult mathematical procedures, and yet it's the beginning step of beginning to locate patterns and structuring the data. There's a lot of software packages. One that I'm familiar with, and it's the one that I've used in some of my work, is that which is called Tinkerplots. And once you become familiar with the software, they can walk you through it. I've seen it used with students who are in 3rd grade, 4th grade, and I've seen them use it with students who are 10th, 11th, and 12th grade. And there are other ways. Another piece of software that has instructional guidelines is just using Excel spreadsheets. You can gather some directions and information about entering the data into the table and then putting a particular formula or procedure code at the top of that formula will run the analysis of the data. And then once you start looking at these patterns, and once it starts to become a common practice of always talking about the spread, of always talking about where's the center, of always talking about what's the most frequent, the kids will start to learn how to do that too. Great.
We've got a couple of people who want us to include a couple links of the things you've mentioned here. I'll repeat those. I'm going to ask that while I go through and give some information about where they can find some information on the NSTA website, if you might be able to put a link to maybe the Tinkerplots and to the College Board book that you were talking about in the chat. Would you be able to do that for us?
Yes, I can do the College Board because that's domain. But I think if people just Google Tinkerplots, they'll come up with a website, and what will happen there is you'll be given access for a trial basis because it is a commercial product. I wouldn't feel comfortable putting it up myself without their permission.
Very good. All right. Well, then I'm going to move us on here just to point to a few little things here, and then we'll get you off to your the survey. And Rick and I will try to stay for a few minutes after to give a little answers to some questions after you do your survey. And so the NSTA website has a lot of information about the standards. nsta.org/NGSS will get you directly there. We're continuing on our series of all the different practices, as you can see here. Next time we'll be talking about analyzing and interpreting data. That's October 9th, 2 weeks from today, same bat time, same bat channel, with our presenter Ann Rivett from Teachers College. Reminder again that we have graduate credit available for these web seminars if you attend all 8 of them, or if you view the archive and answer a reflection question. We will get the archive and the reflection questions up for you tomorrow, if not sooner. You need to do some registration costs, and there's more information at Shippensburg University's website about how this all works together. The conversations we're doing here will continue at the Next Generation Science Standards Forum in the NSTA Learning Center Community Forums, and we've had the link for that go up several times tonight. We'll get them again. And want to point out we've got our 3 conferences, area conferences this fall. The Louisville conference is coming up in just another week or so. We'll be doing Atlanta in November 1st through 3rd, and our Phoenix area conference December 5th through 8th, I'm thinking. I'm having trouble reading the text on my slide right now, but the first week of December. And finally, we've got, you can get copies of the framework itself or a reader's guide at the NSTA store, as well as you can find journal articles on a number of the different practices we've been talking about and other materials related to next generation science standards. And we will be going through the list of people who fill out our survey tonight and selecting someone to get a free copy of the framework. So maybe you'll be the lucky one. With that, I'm going to turn things over to Bryn.
Thank you, Ted. I'd like to take a moment here to thank you and to thank Rick for your fantastic presentation tonight. It was wonderful to have all that knowledge shared and access to the ideas and resources. Everyone, let's use our emoticons button to give Rick and Ted a round of applause. I'd like to also thank the sponsor of tonight's web seminar, the Carnegie Corporation of New York. And I'd like to thank the administration of NSTA for their support for web seminars. And here's a look at our upcoming programs. Tomorrow night we have in our Explorer Vision competition, you can learn how to align the standards and the NRC framework with the Explorer Vision competition. And later tomorrow evening, we have one in our NASA Explorer School series, Engineering Design Process, On the Moon Educator Guide. And then on Thursday, another in the NASA Explorer School series, Engineering Design, Forces in Motion, The Great Boomerang Challenge. And you can register for these web seminars and more by going to our website, learningcenter.nsta.org/webseminars. Thank you, everyone, for your participation, and we look forward to seeing you again on another web seminar soon.